Calculus video 15 on continuity. Specifically, we're going to look at and define continuity at a point. So when a function is continuous at a point, and eventually we'll say that a function is continuous on an interval when it is continuous on all the points within the interval. That would be the definition of continuity on an interval, but it all goes back to being continuous at a point. So let's define this. A function is continuous at point A, right? So at a particular point A, if the following three items occur. One, and you should know this definition, I could ask this one, f of A exists. In other words, the function value exists, or the y value exists at the x value of A. If you're kind of drawing a picture, what that's talking about is at A, there is a y value, meaning the y value exists somewhere at the x value of A. So this is f of A. This is the point, in fact, A, f of A. F of A exists. There is a dot there. It's not a hole. It's not missing. It's not an asymptote, right? That point does exist at A. Two things for the function, or number two, for the function to be continuous at point A, if the limit as x approaches A of the function exists. And remember, when we say the limit as x approaches A, that's the overall limit. So we're saying the limit from the left exists, the limit from the right exists, and those two things equal each other. That's what it takes for the overall limit to exist. So number two here says that at A, the limit exists, meaning the limit from the left must equal the limit from the right. The two limits, the left-hand limit and the right-hand limit, come together, therefore the overall limit exists. And the third thing for the function to be continuous at point A is that whatever value we got for the limit as x approaches A of f of x, must equal f of A. In other words, you have A, or x value of A, and you have some sort of limit, right? You have the limit exist there, the function exists there, and the function f of A exists at the same spot as the limit. Therefore, at A, that function is continuous. You could draw the point, right, without picking up your pen. You could draw the curve without picking up your pen at A. That's what it takes. Those three things are what it takes for a function to be continuous at point A. What I like to do here is to draw a few pictures about what might not happen, what might not be continuous at A. So for example, if I just give you, say, this curve, and I ask you, is f continuous at A? You would say what? You would say no. Why not? You would say because f of A does not exist. There is no value at A. There's no y value at A. F of A does not exist. There's a hole in the graph there. Okay. What if I drew this picture? And now I have some other functions here, and now this is my point A, and look at that, f of A does exist. What we see here is f of A exists, it's right here, in the point A, f of A. We also see the limit exist as we approach A, right? So we approach A, the left-hand limit and the right-hand limit are both going to the same y value, L, whatever this is. But this is not a continuous function at A. We would say, so is f continuous at A? Again, the answer is no. Even though the function exists, the blue dot down there, even though the limit exists, the two are not equal. So no, because the limit as x approaches A of the function does not equal f of A. That would be not continuous at A. Other examples of not continuous. Right, if I have, say, a jump in the graph, that would also be not continuous. The function exists today. It exists right up here in the closed dot. But the limit does not exist today, right? The left-hand limit and right-hand limit are not coming to the same thing. Therefore, the overall limit does not exist. And so we would say not continuous because the limit as x approaches a of the function does not exist. Maybe one more. Let's try the one where we have a vertical asymptote at A. Does that create a problem? Yes, it does create a problem. Not continuous. A couple of things are wrong with this one. One, f of A does not exist. There is no y value here. There's no point at A, right? It's a vertical asymptote, which means it's not defined there. The overall limit does not exist. So already 2 strikes against it. And if those 2 things don't exist, there's no way they can be equal. So this one actually fails all 3 categories. So there you go. There's the definition of continuity at a point. And a few examples of functions that are not continuous at point A. What would a function look like that is continuous? Well, if you had, say, just a function like this, actually we could do this. We could say, look, it's got a circle there. It's got a jump here, right? But because we're only looking for continuity at a point A, we see that the function is continuous. The y value exists, the limit exists, and those 2 things are in fact equal. So we see that the function f is continuous at A, even though it's not continuous at other points along the way.